So today we're going to pick up where we left off. So we saw last time is that we can relate matrix elements that we're interested in computing, both because they're interesting in their own right, and we can relate them to the observables, observable cross-section and decay rate. And so what we saw last time is that we can relate these matrix elements that we're interested in computing to time-ordered expectation values of fields in the Heisenberg picture. And so what we're going to do today is learn how to compute these time-ordered expectation values. And we're going to do that using perturbation theory. So it's going to proceed in a few steps. First thing we're going to do is go to the interaction picture and relate Heisenberg picture time-ordered expectation values to interaction picture time-ordered expectation values. So we'll use basically everything you wrote in your homework yesterday about the interaction picture to do that. And then we'll get an expression that involves Dyson's formula for the time evolution operator in the interaction picture, which we can then expand in a series, and each term in the series we'll be able to compute using Wick's theorem by relating the expectation value of lots of fields to the time-ordered expectation value of two fields. And this is something, this quantity here is known as the Feynman propagator. That's something you almost computed in your first tutorial without the time ordering symbol there that you did compute it. So, well, you could just combine your results for the cases where x naught 1 and is greater than x naught 2 and vice versa. There'll be so the last thing we'll do today is write a simple expression that combines those two terms in terms of a contour integral. Okay, so that's where we're going. Okay, and so to recap very briefly what most of you wrote in your homework. So as we all know, in the Heisenberg picture, states are constant and the operators evolve in time. I'm going to do something slightly different than what many of you did in your homework. I'm going to choose the reference time in which the Heisenberg and Schrödinger pictures agree to be some t naught instead of 0. It's conventionally or often chosen to be 0. Many of you did that in your discussion. This will slightly simplify our discussion to choose the time in which the Heisenberg and Schrödinger pictures agree to be some t naught.
Sorry, which you each the minus I h.
Oh, so, let me. Yeah, two minus signs. There should be this one should be a sign. Okay, so and then in the Schrödinger picture, states evolve and the operators are constant. And the interaction picture is what we'll be mostly interested in today. So in this interaction picture, both the states and the operators evolve. The states evolve with a factor of the free Hamiltonian compared to the Schrodinger picture states, so an extra factor of e to the iht, or we can write them in terms of Heisenberg picture states as e to the ih naught t minus t naught, e to the minus ih p minus t naught, and psi at t naught. And the operators, and this is where most of the simplicity of the main reason why we're going to the interaction picture is the operators in the interaction picture just evolve with the free Hamiltonian. And so in the second lecture, we determined the time evolution of our field operators for the free Klein-Gordon theory. So if we go to the interaction picture, the field operators will evolve in time in exactly that same way that we derived in lecture 2. So we know the time evolution of the field operators. And that means we can compute things like these expectation values. So this is the key property that makes the interaction picture simple for computing things in practice. And the other key point to keep in mind here is that all three pictures agree at t equals t naught. So at t equals t naught, the states and the operators take exactly the same form in all three pictures. And we'll use that agreement between the pictures in a few places today. Okay, and so just so we can agree on notation, most of you wrote something very similar to what I'm about to write, but in a variety of notations in your homework. So what we're going to do, most of our discussion so far has been, or at least in yesterday's lecture, was in Heisenberg picture. So we want to go from the Heisenberg picture to the interaction picture. And to do that, we need to, particularly we're interested in relating these two quantities in the Heisenberg and interaction pictures. And so what we need to do is relate our field operators in the Heisenberg picture to the interaction picture field operators and the vacuum state in the Heisenberg picture to the vacuum state in the interaction picture. And our field operator, Heisenberg picture, according to this relation, well, this relation tells us the relationship between the interaction picture operator and the Heisenberg picture operator. So we can just use that for our fields. So our fields, if we just invert that, we get e to the I h. So this is an h naught. To the I h this is the Heisenberg time evolution. Then if we just invert this relation, we get e to the, or use that relation, we get e to the minus I h naught t minus t naught times the interaction picture field times e to the I h naught t minus t naught e to the minus I h t minus t naught. That's a minus times e to the. Okay, so for our, I'm mostly going through this to establish notation. So this is the interaction picture field. And because this combination of factors is going to show up repeatedly, I'm going to give them a name. So I'm going to call this U dagger of t naught, phi naught, x, and t times u t naught. So u is just this exponential of the free Hamiltonian times this exponential of the total Hamiltonian. And this is, u is the time evolution operator in the interaction picture. And the formula for the time evolution operator is what you wrote in your homework and what you saw in the quantum theory course. So it's given, I'm going to introduce some shorthand notation. So instead of writing u of time evolution from t1 to t2 all the time, I'm just going to write subscript 1 and 2. And this is given by the time ordered exponential of minus I times the integral from t1 to t2 dt prime times the interaction picture, interaction Hamiltonian. And I should have mentioned before, but here we're assuming that the Hamiltonian is some free part plus some interaction part, which I'll call H1. And in a sense, we'll assume that the interaction part is we can treat as a perturbation. So far, nothing. We haven't made any assumptions that H1 is a perturbation, but that will come in at a point that I'll mention later.
Sorry.
Yes.
The interaction field is sandwiched in the middle here. Are they all evaluated at t or t naught? Like, is this the priority time?
Evolved from, yes, this should be from t naught. Sorry. The here?
Does that not also indicate that it's evaluated at?
This not, this subscript 0 here indicates that it's the interaction picture field. So the interaction picture field evolves in time. The Heisenberg picture field evolves in time, and they evolve in time differently. At t naught, they're the same. This is a time evolution operator, so if we evolve for no time, this operator is 1. So this is a time evolution operator, which means that time evolution for no time is the identity. It's unitary. So U21 inverse is U21 dagger, which is the same as evolving backward in time. And the course, if we expect the time evolution operator to obey a composition property, so if we evolve from time t1 to time t2, and then from time t2 to time t3, that should be the same as evolving from time 1 to 3 directly. So u13 is u32, u23, 21. You could have verified these explicitly using this formula, but I won't do that. That's just what you'd expect. For a time evolution operator, it should obey a composition. Evolving for no time evolution is the identity. And it's unitary. Okay, so that's a extremely fast review of the interaction picture, but you're all familiar with it from both your homework and the quantum theory course. So what we're going to do now is basically just express our Heisenberg picture vacuum expectation value of the time order product of fields in the interaction picture. So we already know how to express the fields in the Heisenberg picture in terms of the interaction picture of fields. So what's left to do is express the vacuum state in the Heisenberg picture in terms of the vacuum state in the interaction picture. And this should be a 0. Okay. So the next thing we're going to do is determine the relationship between the vacuum state of our interacting theory and the vacuum state of our free theory. And so in a slight abuse of terminology that's used everywhere, I'm often going to refer to the interaction picture fields as free fields because they behave like free fields. They have the same time evolution as the free fields. So if you hear me say free fields, really we're throughout today's lecture, we're working with an interacting field, but most of the time we'll be working in the interaction picture. And interaction picture fields behave just like free fields. So I'll often use those terms interchangeably, even though they mean slightly different things. It's a very, very common way of referring to the interaction picture fields. I'll denote with the subscript 0. And so, yeah, so implicit in that is that we're basically always going to choose H0 to be our Klein-Gordon Hamiltonian, or the complex version if we're dealing with a complex scalar field. Okay. So basically the main thing left to do is determine the relationship between these two vacua. And so what do we know about the interacting vacuum? Well, the interacting vacuum should be annihilated by the annihilation operators. So in particular, we should have that AP at T0 react on. So here we're working the said we'll mostly be working in the Schrodinger Heisenberg picture, but here working the Schrodinger picture. So if we take this operator at this time and act with it on the Schrodinger picture vacuum, we should get 0, at least for t equals plus or minus infinity. We can also express this as e to the minus I h t minus t naught. Omega should be 0. So this is just saying that our annihilation operators annihilate our vacuum state. And well, so this is a statement about the interacting theory and the interacting vacuum. Make similar statements about the free vacuum. So if we act with, write the same sort of equation, Schrodinger picture, act with the annihilation operator on the time-dependent vacuum of the free theory, should get 0. We write out the time evolution explicitly. This equation becomes e to the minus I h naught t minus t naught, acting on 0, should be 0. And now we can use this property that all three pictures agree at t equals t naught. So we can interpret, so the annihilation operator at time t naught is the same in the Heisenberg picture, the interaction picture, or the Schrodinger picture. So these are the same operators. And so we have here two different states that are annihilated by all of the annihilation operators. And basically, that's what we mean by the vacuum, at least up to some normalization. A state that's annihilated by all of the annihilation operators has no particles, so that's what we would call the vacuum state. So up to some normalization, this state and this state should be the same. So we should have, at least if we assume that the vacuum is unique. There could be multiple distinct vacuum states. We're just going to assume that the vacuum is unique. Then we should have that e to the minus I h t minus t naught. Omega is proportional to e to the minus I h naught t minus t naught, 0. This means it's proportional to, so there might be some normalization constant that's different. Well, we only assume that this was true for t goes to plus or minus infinity, so this will only necessarily be true for t going to plus or minus infinity. And so that tells us that omega is some normalization, which I'll call n sub I, times the limit as t goes to minus infinity, e to the plus I h t minus t naught, e to the minus I h naught t minus t naught times 0. But this combination of exponentials is precisely what we called time evolution operator. So we can write this as ni u 0 minus infinity 0. Vivian?
How did you go from the second to third line?
So so here, this is the vacuum of the free theory in the Schrodinger picture. It evolves in time, just by a phase.
The line above that to that line. Yeah, there or
this line implies this line implies that line.
So you're saying that they basically have to be the same because they're both annihilated by the annihilation operators.
At least, sorry, go ahead.
Isn't that exactly what you assumed on lines 1 and 3? Like, I don't understand how you should. Like, you assume on the first line that the annihilation operators kill the interacting vacuum, and then on the third line you assume that it kills the free vacuum.
Yes. So what I was using is that all 3 pictures agree at t equals t0. So the interaction. So if we're working in an interacting theory, this is just the statement that the vacuum is annihilated by all things. So in this third line, though, I noted that at the time t equals t naught, the interaction picture agrees with Heisenberg picture. So we can also make a statement about the free theory at that one time.
What's the NI?
Is that U dagger?
Is this U dagger? Did I make a sign mistake somewhere? Okay, the signs. That should be a. E minus T naught.
Something I don't understand. There, when you replace the interacting picture vacuum, shouldn't you replace it with that line there? That is I, H naught, and not minus H. When you replace the interacting vacuum.
Here?
Yep.
So the interact. So here we're in the.
That's
this is a Schrodinger picture going to the Heisenberg. I think I answered your question. I must have made a sign mistake somewhere. I want this should definitely be the time evolution from minus infinity to 0. Where I made the sign mistake. Let's see. So I multiply. I don't see it right now. Yeah. I can track.
Sorry.
Yeah, in the previous formula you were evolving from T naught to T, but here you are evolving from T to T naught. Yeah, you're setting T to minus infinity.
But those still don't commute, so that doesn't fully solve the problem.
So yes, okay. So but we do have the fact that it's unitary. So if we can switch the order and flip the arguments. So I think that's what we use.
Okay.
I think it should be correct as is. I use this.
My other question is for the first line, when we say that this is true for t is plus or minus infinity, is that saying that if you go to t equals plus or minus infinity, you're assuming that the vacuum states are the same in both pictures, or?
Essentially, that's basically what we were assuming when we derived the LSE formula yesterday. Okay, so we have this relationship between the free and interacting vacua. We can also write the relationship in a slightly different form that will be useful. So here we consider the minus infinity limit. We consider the t goes to plus infinity limit. We can also write omega as some different, a priori different normalization constant times u infinity 0 acting on 0. So we have two different relationships between the free and interacting vacuum. All right, and it'll be more convenient. This should be 0 infinity. It'll be more convenient to look at the raw version of this equation. Oh, so like this. Okay. So that's basically everything we need in order to go from the Heisenberg picture to the interaction picture. What's left basically is just to combine our results. And we'll find some nice simplifications. Okay, so what we're interested in computing is Heisenberg picture, expectation value of some time-ordered product of fields. And for simplicity, let's assume that everything is already time-ordered. Then we can just forget about the time ordering symbol. And what we get is, so you get a factor of Ni and Nf in going from the, in relating the interacting vacuum to the free vacuum. And the interacting vacuum becomes 0, u infinity 0. Then we have here the Heisenberg field operator, which we can relate to the interaction picture field operator, again with u 0, 1. So here I wrote it as u dagger. So this is u dagger. t0, I can just use the fact that this is unitary to write this as u of t naught and t. So this gives us this expression, the 1, 0. And we have u 0, 2 phi naught of x2, u2, 0, and so on, up to un 0, u 0 minus infinity, 0. And, well, we see we've got lots of products of time evolution operators. They're time evolution operators, so evolving for some time interval and then a second time interval would be the same as just evolving for the entire time interval at once using this composition property. And simplify this. We get ni and f 0. This collapses to u infinity 1 by 0 of x1, u2 by 0 of x2, and so on, up to un minus infinity, 0. And so this is already time ordered. So I'll put back the time ordering symbol. And if there's a time ordering symbol here, we can move around these time evolution operators and bring them all together and use the composition property repeatedly to collapse u infinity 1, 1, 2 to u infinity 2, 2, and the 1, 2 will collapse to the 2, 3, and so on until all we're left with is time ordered product of phi naught x1 up to xn u infinity minus infinity 0. So we're almost done. The only thing left to determine is this normalization factor. And, well, we can determine that by choosing a normalization for a vacuum. So in the free theory, it was convenient to choose a unit normalization for the vacuum. That will, again, be a convenient normalization to choose. So if we demand that our vacuum is unit normalized, that tells us that 0 times u infinity minus infinity, 0 times ni and f is equal to 1. So ni and f is 1 over u infinity minus infinity, 0. Alicia.
Are we assuming that the interaction Hamiltonian does not depend on the momentum? Because we're assuming that they commute with the phi's, right? With the fields?
We're not assuming they commute. We're assuming, so this expression is already time ordered.
Yeah.
So I'm not changing it if I add the time ordering symbol.
Yeah, but there are operators in the middle of two phi's. Like,
This.
yeah.
But if I don't change this expression by adding the time ordering, then I'm free to move these time evolution operators together inside the time ordering. I can rearrange things, and the time ordering tells me I should put them back in the same order because this is the time ordered version. So without, I agree, going from this line to this line without the time ordering symbol would be problematic. But the time ordering symbol says, okay, whatever operators we have here, we should put them in time order.
Could we have done this same derivation just without getting rid of the time ordering in the first step? I mean, we could have done everything the same.
Yeah, we could just leave it here
Yeah.
if you're happy with that.
Yeah. Just yeah.
So does time ordering like also allow you to arbitrarily commute anything?
Yeah, yes, basically it tells you you can move things around however you like, and time ordering says when you're actually going to compute them, you should put them in the time order. It's just like the same reason inside a normal ordering symbol, you can move the operators around however you like. The normal ordering symbols tell you that there's a prescription, or if you actually want to calculate them, that what's inside of the normal ordering should be evaluated in a particular order.
But aren't there some commutation relations that are independent of time?
Yeah, this going from this step to this step doesn't work if we don't have time ordering, because these operators don't commute. But with the time ordering, it's okay. Okay, so you're kind of first.
We need to be careful if there are multiple operators that are evaluated at the same time. Like the time of operation would be this case.
So if there are multiple operators at the same time, then we should be able to put the operators at the same time in either order. So in that case, there could be ambiguities if operators at the same time don't commute.
Doesn't that make them economize? Just switch things around.
Yeah. So to avoid or deal carefully with subtleties involving operators going to the same point, coincident limit. Actually, not only here, but also in what we did in the LSD, there's some subtleties when the operators approach the same point. You can, to deal with those carefully, you should do the whole derivation using wave packets. And that can, the end results will be the same. Derivations are much more complicated. But if you're worried about that point, that's what you do.
The U's depend on 2 times.
That's right.
So what does it mean to time order them when they?
Well, we can think about these U's as exponentials. So it involves the Hamiltonian at a bunch of different times. So we're basically, it gives us, if we're thinking about an integral as a limit of a sum, we're doing that sum in a particular order. Or yeah, the operators, if we, or more explicitly, if we're Taylor expanding this out to second order, that tells us something about. So the linear term here, when we Taylor expand that, everything's already time ordered. The second order term, this time ordering tells us to put the Hamiltonians in the 2 different integrals in a particular order.
So, like when you're lifting up the U's over here and moving them around, like really there's all this going on in the background where you're moving the Hamiltonians around.
That's right. That's all going in the background. So we wouldn't be allowed to just move things around if there wasn't the time ordering symbol, but there is. So we can move them around to make it simple, and then in the end, when we're actually computing it, we have to remember that in our explicit expressions, everything is time ordered.
So, sorry, one last question. The last U that you're left with from minus infinity to infinity, how do you know to put that on the right-hand side of all the phi's and not?
It wouldn't matter. We could put it on the left, in the middle, wherever you like. We can also move these around however you like. This is.
But like, say, if you got rid of the time ordering there in the last line,
then yeah, that would be problematic. Because we wouldn't then be justified in moving everything around like we did. Okay. In a sense, the fact that we're allowed to move things around in time ordering is the same as the statement that this is, if we normal ordered, like these operators don't commute, but inside a normal ordering system, we can commute. Same thing for time ordering. So our final expression, our almost final expression, is that this vacuum expectation value is T, that's the free fields, times the exponential of I times the integral of H, the interaction picture, interaction Hamiltonian, all divided by just the time ordered expectation value of the exponential. Minus I. And I call this almost a final expression. We could use this. We could go through and compute the Hamiltonian every time we wanted to do perturbation theory. When we start, when we specify a theory, we're specifying Lagrangian, so it would be easier if we, instead of having expressions here involving Hamiltonian, if we had something involving Lagrangian. And we can do that. So we know that this time evolution operator is T times the exponential minus I integral of the interaction picture interaction Hamiltonian. And the interaction picture Hamiltonian is just related. So assuming that for the cases we're interested in, our interaction term is always just going to be a power of the fields. So if we want to go from the Heisenberg picture to the interaction picture, then what we'll have, so suppose that H1 is the integral of some power of fields in the Heisenberg picture. Then in the interaction picture, we'll just get a bunch of time evolution operators on either side, a U and U dagger on each side of the fields. Most of those will cancel. We'll just be left with a U dagger on the left, a U dagger on the right, which is basically tells us, which is how we would expect the interaction Hamiltonian to be related in the Heisenberg and interaction pictures. So that means that the interaction Hamiltonian in the interaction picture is just equal to the interaction picture, the interaction Hamiltonian in the Heisenberg picture, just with all of the Heisenberg picture fields replaced with free fields, interaction picture fields. And so that tells us, and so all we need to do is just replace phi with phi naught. And so a simpler way to write this time evolution operator is as an integral over the interaction Lagrangian as a function of free fields, where L int is L minus L naught. So here we're assuming that this is just a interaction Lagrangian is just a function of fields. So then to go, the new term in the interaction Lagrangian would just give us a new term in the interaction Hamiltonian with the opposite sign. That's why the sign changed from a minus to a plus when expressed in terms of Hamiltonian or Lagrangian. But otherwise, we just take our interaction Lagrangian, replace our field Heisenberg picture fields with free fields, and that gives us the time evolution operator in the interaction picture. And so, final expression is that this time-ordered expectation value of a product of fields is equal to 0 times t times the same time-ordered product of fields of free fields, an exponential I times the integral of the interaction Lagrangian function of the free fields 0 over the same thing without any fields. And this is our key result. A key result from today's lecture. And so key point is that in deriving this expression, we have not used perturbation theory yet. So the only basically new thing we've assumed is that the vacuum is unique. But otherwise, we've just re-expressed the Heisenberg picture fields in terms of the interaction picture, or free fields. And this is basically as far as we can go without using perturbation theory. So what we're going to do next is, well, this is a nice expression, but to evaluate it exactly, basically we're going to have to use perturbation theory. So we're going to have to expand out the exponential. So if we expand out the exponential, we'll get an infinite series of terms. Each of them will involve at least, except for the first one, will involve some integrals. And as we saw on the front end, typically when we're doing perturbation theory, and as we'll have to do here, in order to evaluate this perturbatively, what we're going to do is first expand things out, a series expansion of the exponential. Then we're going to swap the sum and the integral. What we're going to get will be asymptotic series expressions for this, which means that we'll be able to compute everything in that perturbative expansion. We'll also be maybe missing things, non-perturbative effects that we discussed somewhat in the front end, and we'll discuss more later.
When you go from the Hamiltonian, the interaction Hamiltonian to the interaction Lagrangian, are you assuming that the L int doesn't change your definition of the canonical momentum?
That's right. I'm assuming here that L int is a function just of the fields, not of their derivatives.
That's always the case.
It's most often the case. There sometimes we'll be interested in cases where we have derivative couplings, but those can introduce additional subtleties. So for the near future, we'll just be focusing on the case. Okay, so at this point, we need to do perturbation theory. So let's do that and see how we can evaluate these time-ordered expectation values that we're interested in. So if we expand our exponential, the terms we're going to get are going to look like 1 plus some integral of the Lagrangian plus f I squared times a multiple integral of the Lagrangian and so on. And so basically each of the terms in the perturbation series for the numerator and the denominator are going to be of the form I've written several times before. They'll be time-ordered products of a bunch of interaction picture. So each term will look like this. So there'll be a bunch of integrals we'll need to do, but those are just integrals that we know how to do. So the remaining work in being able to calculate the right-hand side of this expression is learning how to calculate these time-ordered expectation values of free fields. So that's what we're going to do next.
Sorry. Where's the time ordering done?
It should be a time order. Right, it's a schematic expression. Thank you for catching that. Okay, so and the way to evaluate these expressions is using Wick's theorem. So first I'll state Wick's theorem and then present a sketch of a derivation, where it comes from. So Wick's theorem is a statement that relates time-ordered product of fields, of field operators, free field operators, says the time-ordered product of field operators is equal to the normal ordering of all possible contractions. So all possible contractions here includes partial contractions. And what I mean by contraction is we take a pair of fields, pair of free fields, and we write the contraction like this, or equivalently like this. And a contraction means taking a pair of fields and replacing them by the vacuum expectation value of the time-ordered product of two fields, or also known as the Feynman propagator. So all possible contractions here means this includes terms that are completely contracted or not contracted at all or anything in between. So contracting anywhere between 0 and n over 2 fields if the n is even. So what the statement means, for example, explicitly, if we looked at the time-ordered product of 3 fields, and I'm going to introduce some shorthand notation. So basically, from now on, unless otherwise specified, we'll be working with the interaction picture free fields. So here, phi 1 means the interaction picture field of x1. So if we look at what this statement says is that time-ordered product of 3 fields is equal to the normal ordered product of 3 fields plus the normal ordered product of the 3 fields with 1 and 2 contracted plus the normal ordered with 1 and 3 contracted plus the normal ordered product with 2 and 3 contracted. Those are all the partial contractions. We can contract no fields or 1 pair of fields. There's no way to contract all 3 fields. So that's what the statement means. So really, maybe it should be the sum of all possible contractions. Okay, and the reason this is useful is that a normal ordered product vanishes inside a vacuum expectation value as long as we have any field operators, right? So Wick's theorem is a statement about the operators, but we're ultimately interested in computing our vacuum expectation values of operators. So Wick's theorem will tell us that we can replace this time ordered with a normal ordered sum of normal ordered terms, and the vacuum expectation value of some normal ordered terms vanishes unless we have a completely contracted term. So a completely contracted term will give us a product of Feynman propagators. So Wick's theorem says we get a bunch of terms. In practice, the only terms we're interested in are the completely contracted terms. Okay, so where does this come from? So it's useful to break up the field into 2 parts. One I'll call phi sub plus will contain the creation operators. If we want to relate time ordering to normal ordering tells us is a prescription for ordering the creation and annihilation operators. So we should express our fields in terms of creation and annihilation operators. And say the phi plus is the part that contains the creation operators. Phi minus contains the annihilation operators as a minus sign, the exponential. So I'll use this notation. Some of the newer references use this notation. If you look at any of the older references, they'll define everything in terms of phi plus upstairs and phi minus upstairs, which are flipped. That plus and minus in that case refers to positive and negative frequencies. I think that's less intuitive than this. The plus has the plus sign in the exponential and has a creation operator. I'll use this notation. And okay, so given this, we can compute the time order product of two fields and write it out and try to relate it, the time ordered product, to the normal ordered product. So if we expand out the time ordered product, there'll be 4 terms. And let's assume here that x0(1) is greater than x0(2) for concreteness. So in that case, if we expand this out, we get phi plus of x1, phi plus of x2, phi plus, phi minus of x1, or let's say plus and phi minus of x2, get phi minus of x1, phi plus of x2, and phi minus, phi minus. And most of these terms are already normal ordered. Remember, normal ordering means put all of the creation operators to the left, annihilation operators to the right. This is normal ordered. This is normal ordered because the creation operators to the left. This is normal ordered. There's only annihilation operators. So this is the only term that's not normal ordered. And we can rather easily fix that just by using the commutation relations. And so we can write this as the normal ordered product plus commutator. So if we switch that, we'll just get the commutator of phi minus x1, phi plus x2. And in the opposite case, we'll just get the opposite commutator. And so what we get is phi 1, phi 2 is the normal ordered product, phi 1, phi 2, plus phi minus x1, phi plus x2, times theta of x1 naught minus x2 naught, plus the opposite commutator, phi minus x2, phi plus x1, theta of x2 naught minus x1 naught. And claim that we'll justify later is that this long expression here is equal to the Feynman propagator x1 minus x2. Okay. And so that's a proof for the case of two fields. For n fields, we can use induction. I'll just sketch how it works. So in general, use induction. Assume it for n fields, or n minus 1 fields. And let's also assume that, without loss of generality, that T1 is the latest, or x01 is the latest time. Then we have that T of phi 1 up to phi n is, well, we can use the fact that this is time ordered to write this as phi 1 times the time ordering of the rest. Write this as phi 1 times the time ordering of the rest. Time ordering of the rest is, by Wick's theorem, for assuming holds for n minus 1 fields, is the normal ordering of the sum of the contractions of phi 2 up to phi n. And write this as phi plus x1 plus phi minus of x1 times this sum of contractions 2 to n. And this term is already normal ordered. So we can just bring the plus part inside the normal ordering symbol. It involves a creation operator. Creation operator should be to the left. We don't care what order they're in inside that. So that we can bring that inside. And so the only thing we have to worry about is this phi minus. And what's going to happen if we try to bring this phi minus over to the right? Well, every time it moves past a phi plus from one of the other fields, we're going to have to introduce a commutator term. And that's basically going to give us a contraction. This delta, this Feynman propagator, can be expressed in terms of the commutators of phi minus with phi plus. So every time we move, so we'll create a contraction by moving it past the phi pluses. And this contains all possible contractions, including every possible way of having the phi pluses uncontracted. And then we'll get all the contractions with phi 1 from the commutators of phi minus of x1 with the phi pluses of the other x's.
Are all of these implicitly sandwiched between the vacuum?
Wick's theorem is a statement about operators. So it holds even as an operator statement. We're interested in it most often in the case where we're sandwiching between vacuum. So if we sandwich it between vacua, the vacuum state, then most of the possible contractions will vanish. The only ones that will survive are the completely contracted. Okay. So I won't be more explicit here, but hopefully it's at least plausible to you that if you do this, you'll get all the possible contractions. Okay. So yeah. So yeah. The last thing.
Sorry, I'm confused with the notation because there you define the contraction as something you have to put into, well, you have to take the expectation value in the vacuum.
Okay.
Wick's theorem.
Wick's theorem. Okay, so there are a number of different expressions for the Feynman propagator. One is that the Feynman propagator is equal to this vacuum expectation value. There is an operator expression for Feynman propagator. So this in the blue box is another expression for the Feynman propagator. This is you might expect that this is an operator. If you compute these commutators, what you'll find is that, in fact, this is a number, not an operator. So the vacuum expectation value of this thing in the blue box is equal to this operator. So the vacuum expectation value just doesn't do anything. This looks like it should be an operator in general. Take a commutator to operators and generally get an operator. For this special case, because we're in a free theory, we get a number instead of an operator. So I could write an operator expression over here instead of a time vacuum expression. Okay, so the last thing to compute is the Feynman propagator. And so Feynman propagator has a few possible definitions. And define it to be this time-ordered product of two fields. And it's called the propagator because we can think about this as like the overlap of the one particle state, phi of y, propagating to the one particle state, phi of x acting on the vacuum. In that sense, it's a propagator. And basically, this is, if you remove the time ordering, this is something you already computed in tutorial 1. And what you found was that this is equal to the integral that. So all we need to do is combine this expression with the x and y, the expression with x and y switched, multiplied by some Heaviside functions.
But that field is the field in the Heisenberg picture, right?
Yes, this calculation, but it was in the Heisenberg picture for the free theory. And so the interaction picture fields for an interacting theory behave just like the Heisenberg picture fields for the free theory. So we can carry over our results directly. They evolve in time in exactly the same way. That's how we define them. That's why we're using the interact. So delta of f can be written, get two terms. So we get here this term if x naught is greater than y naught. And we can also write it, I'm going to write it in a slightly funny way, the other term. So the other term should just be the same thing with x and y flipped. So we're going to write it as 1 over 2 EP, e to the minus I, e dot x minus y. Times this. Evaluated at p naught equals minus EP. And this term, of course, implicitly, as we've been doing all along, it's evaluated at P naught equals EP. There's an extra minus sign here. Minus. And so what I've done is this term should have just been have x and y switched. But I'm allowed to flip the measure, flip the sign, take p to minus p. And that doesn't change the measure. So that would just change the signs of the spatial components. I can change the sign of, undo the change of the sign of the time-like component by just evaluating this at minus EP instead of EP. And, well, so convenient way to write this is as follows. And I'll explain where this comes from in a minute. It'll be easier to think about going backwards. We can write it like this. Write it as a contour integral or some contour CF. So a contour integral in the complex P naught plane. So here, let me sketch what we're doing. We've got the real part of P naught, the imaginary part P naught. This integrand in the last line here has two poles. It has a pole where P naught equals EP or P naught equals minus EP. And this contour CF is a contour that goes around these poles as follows. This, so it goes below this pole and above that pole. And so to see that this line gives us the same thing as the line above, we could complete the contour in two different ways, depending on whether x naught is greater than y naught or y naught is greater than x naught. So if x naught is greater than y naught, then we have here a minus I times P naught times x naught times a positive number. So minus I times P naught times a positive number. So we want, if we want this exponential term to go to minus infinity, we should complete the contour in the lower half plane. So we should complete the contour like this if x naught is greater than y naught. And in that case, the value of this integral is equal to the residue at this pole, which is just this expression here. And in the opposite case, we should, if y naught is greater than x naught, we should close the contour in the opposite direction. Imagining a contour that is a large semicircle in one direction or another. And this minus sign just accounts for the fact, takes care of whether we're going clockwise or counterclockwise around the pole. So that this expression is equal to this one, which is just what you computed in your tutorial. And this will be the most convenient way to write the Feynman propagator. It's sometimes abbreviated as d4p over 2 pi to the 4 I over p squared minus m squared plus I epsilon e to the minus I e dot x minus y, where this I epsilon is an equivalent way of specifying the contour. It's just imagining you're adding a small positive imaginary part to the denominator, which would shift this pole down a little bit and this pole up a little bit, and then you integrate along the real lines. So this here is the form of the Feynman propagator we're going to use to compute the first the time-ordered expectation value of free fields, which we can use to compute the time-ordered expectation value of interacting fields, and use to compute matrix elements. So this is the Feynman propagator, and well, one key property, or one useful property of the Feynman propagator is that it's a Green's function. Or the Klein-Gordon operator. So if we act with Klein-Gordon operator on the Feynman propagator with its derivative x with respect to x, what we get is we just bring down a factor of p squared minus p squared from the x derivatives. And so we get I over p squared and m squared I epsilon times minus p squared plus m squared e to the minus I e dot x minus y, which this just cancels off, and we're left with minus I e times the integral of e to the minus I e x minus y, which is just minus I delta. So this is a Green's function, and we'll use that that fact when we're explicitly computing these propagators, and you'll examine this property in related Green's functions in tutorial this afternoon as well. Any questions on? Okay. I'll see you this afternoon.